Welcome, welcome, welcome to chemistry. So you're getting to see me again. I'm back. We're going to review for the test. You're going to have a test on Monday when you come back in chemistry over what we've been learning the whole time, the periodic table. But before we do that, I wanted to say that some of you have not been doing your homework. And I have my door open because Miss Raymond's going to be coming in a minute and I don't want to lock her out. But anyway, I can check on Plasma Games and half of you have not played. And you have to play 2 levels. And I can see what you've played and how long it took you to play, all of that. And I'm old and I did the game. I did 3 levels in 30 minutes. So I know y'all can do this. So do the Plasma Games. It's going to help you with this periodic test, learning some of the properties of metals, and it will help later when we do gas laws. So do it. I know it's kind of cheesy, but do it. Play that game. And then the other thing is I can tell what you've done on build an atom. So do the build an atom. Don't just try to answer the questions. You have to go in and play that game, play that simulation. Also, on it, some people are not understanding that where you click atoms, you get to the atom simulator. Next to it, there's 2 squares over it says games. That's where you play the games. And they're fun. And like I said, if I can do it, I know you can do it because y'all know more about video games than I do. Though I do play Animal Crossing. I'm queen of Animal Crossing and I like Legend of Zelda. All right, so I play video games every day actually, but I just don't play hard challenging games. I play easy games. The ones you played probably in elementary school. Anyway, reviewing for the periodic test so that you're gonna have on Monday. So this is normally where I would say, okay, we're gonna play rock, paper, scissors. So you can play rock, paper, scissors if you want to. Now, this is how I think you should use this video. I'm gonna be going over things that are like the test questions. So I'll be asking questions and then I'll answer the questions. I think if I were you, what I would do is I would pause it after I ask the question, then I'd pretend like it's my question and pause it and see if I could answer it, and then push play again and see if you got it right. I think that'd be a great way to study for this test. We've really spent a lot of time on this, more than anything else we've done, so I think y'all are gonna be great on it, but I wanted to make sure you had your review. So this is your homework for Friday. I'm posting this to review for the test and to study for the test and to use this video for the test. All right, whew. Okay, next. All right, so the first thing, and I meant to bring my Muppets book, but I took it home and I forgot it. But remember when I read you the Muppets story about people in my family? Okay, so this is what the test question would be like. It would be something like, which are more alike? Helium, neon, and argon, or neon, fluorine, and oxygen? And do you remember? It's the columns are more alike. Oh, do you remember? Now hit pause. Now I'm back. Now push play. And remember the answer is that the columns are more alike. That periods make it where families have similar members, but families or columns are more alike than the similar members. And like they're similar in that, like if you look at the noble gases, the smallest one, well, we could go over here to oxygen family. That the smallest one is so small that it's a gas, and the same thing is true over here with this family. The smallest is the gas. So they have similar members, and you know, down here these are very heavy and radioactive, and down here this would be very heavy and radioactive. So it has similar members, but the families are more alike than, I'm getting my water, extreme close-up. The families are more alike than their members are. So that's the first thing you need to remember. Now I'll put my water down. Okay, this is a very casual video. In and out. I feel like it's the old Batman from the 60s. Da-la-da, da-la-da. All right, focus, Lisa. Miss Blackburn. Anyway, we talked about that. Okay, why are they similar, more similar like families? You can push pause and then try to answer. Why are the families more similar than the periods? It's because they have the same valence electrons. And do you remember how to count how many valence electrons it has? You go to the period and count. So like over here, hydrogen has one valence electron. Helium has 1, 2. Lithium has 1 because it's one space over. Beryllium has 1, 2. Oxygen will do it. 1, 2, 3, 4, 5, 6 valence electrons. So make sure you know how to count over to see how many valence electrons it has. And also remember, those are just the outermost ones, and those are the ones that give it its properties. That leads into what we're going to do next. On Monday and Tuesday, for those of you who are, whichever day you're supposed to come. And then Wednesday and Thursday, we're going to do labs into our next thing, which is bonding. And we will be counting those valence electrons again. We're going to do something called Lewis structures, and it's going to be fun. You'll like it. All right. We talked about that. Okay. Already showed you that. Okay, so now you need to know the difference in a metal, a non-metal, and a metalloid. So pause the video and see if you can think of some properties of metals, then non-metals, and metalloids. And you also need to know where they are on the periodic table. Okay, now I'm back and I'll tell you the answer. Metals are the things from the stair step, the metalloid stair step over. And they are shiny. They're good conductors of heat and electricity. They're malleable, which means they can be hit by a mallet and hammered out into sheets. They're ductile, which means they can be, this is what I always do with my hands, they can be drawn into wires. They have, I'll tell you about that in a second. They make cations. Remember, they tend to lose electrons to feel like a noble gas. And then the nonmetals are up here, and they're brittle. They're poor conductors of heat and electricity. They're dull. They're not shiny. And they tend to make anions. They tend to steal electrons to feel like a noble gas. The ones in the middle are metalloids, and they're sort of in between. They are also brittle, but they can be shiny. They're semiconductors. And they tend to be anions, aluminum though. Anyway, they can be kind of either. They can, but this is the one I want to talk to you about. Do you remember when we talked about how that the periodic table is like the electrons are like children, and the guys over here want to lose their kids, the guys over here want to steal kids, and these in the middle are the hippies, and they let the kids run around wild. And these are the divorced parents who have custody arrangements where they share the kids. Okay, remember all that? And remember, everybody wants to be like Kate and William, and I'm trying to remember the kids' names, Charlotte and George and Louis, the royal family. Okay, everybody wants to be princes and princesses. So now, with that in mind, we talked about electronegativity, and electronegativity is how close they hold on to their electrons. And so these guys over here don't hold on to their electrons at all. And as you go down a column or a family, they hold on to it even less. So this idea of holding on to electrons is called electronegativity. There's other ways you'll learn in college called ionization energy and things like that. But if you basically understand the idea of what they want to do with their electrons on the periodic table from where we talked about them like children, you'll get it. So these guys hold on to their electrons less and less, which means that the ability to hold on to the electrons increases, the electronegativity increases as you go up the families. It's harder for the bigger ones to hold on to their kids. That as you go across, electronegativity increases because they want to hold on to their electrons and, remember, steal someone else's too. So as you go across, electronegativity increases, and electronegativity also increases as you go up, because the smaller they are, they can hold on to their electrons tighter. And if you remember, that is because of shielding effect. Remember, shielding effect is the thing I told you about my sister. Shh, don't tell her I'm talking about her. Where she had a whole bunch of kids. She had 6. And so I would see in her family how they would, that if one of them wanted to do something bad, they'd look and see where mom was, and then they'd make sure there were some siblings between mom and them, because they knew if there were enough siblings there that they'd get away with it. They wouldn't get punished. And it's the same way with the electrons. If there's more electrons between the nucleus, you could think of the nucleus like the mom, and the outermost electrons, then that nucleus has less power over those electrons, that they get further away and they just have less power. And the reason why is because they get shielded by the other electrons that are between that far electron and the nucleus. So that's what shielding effect is. So shielding effect increases as you go down the families. Now, even though there's getting to be more and more electrons as you go across a period, shielding effect really is thought of as to be kind of constant. If there is more shielding effect because there's more electrons, it's not much, because as you go over here, the nucleus holds the electrons tighter. And so even though there's more electrons, the nucleus is holding them tighter because these guys want to keep their electrons and steal someone else's. Then that causes less shielding effect. And imagine that, if a mom got all of her kids real close, even if there's a bunch of them, if one of them's bad, she could whack them if they were out of line, if the mom believed in spanking, which some don't. We're not really talking about real kids, so don't worry about that. Okay, so the other thing that is impactful with this is atomic radii. How big is it? And as you go down the families, it gets bigger because there's just more of them, more electrons make it bigger. But this is the weird one. As you go across this way, the atoms actually get smaller, even though there are more protons, more neutrons, more electrons. The atomic radii, the radius, as you go across, gets smaller, and it's because though you have to always remember, what does the atom want? And as you go over here, they want to keep all of their electrons and steal someone else's. So they're pulling their electrons in closer and closer. All right? So get those little terms in your head. But if you remember what's going on, it's not hard. So the electronegativity, you just have to remember that definition. It is the tendency for a nucleus to attract electrons to itself. Okay. All right, we talked about that. You need to know the areas of the periodic table. So they're over here. I want to go stand over there, but I'll be off screen, so I'll have to reach over here instead. Okay, so you can see this little peach color is the alkaline metals. They're this one. The darker peach is the alkali earth metals. The transition metals are this square right in there. They're kind of army green. The other metals, sometimes they're called base metals, or those light green. The non-metals are the purple. The noble gases are the pink. The lanthanides are on top here, and the actinides are on bottom. And you can always tell that because this one starts with La, and that one starts with AC. So that's what those stand for. This periodic table doesn't have the metalloids marked, but they go on this stair step. And you might have noticed there's some debate about exactly which ones these are. The periodic table I was looking at said it's boron, silicon, germanium, arsenic, antimony, tellurium, polonium, but some of them include aluminum, some don't. So it's and some of them include AT. So but basically they're the ones on the stair step that go across right there. And you won't be asked exactly which ones are. You'll just be asked what region of the periodic table are they and what are their properties. And we said they're semiconductors, they're electrons. So going back over here, talking about characteristics of the periodic table. Over here, these metals have low electronegativity because they can't attract extra electrons to themselves. They want to give away their extras and get no more. Over here is high electronegativity because they want to keep their electrons and get somebody else's. And then the metalloids here are medium electronegativity, that they want to, and they're kind of wishy-washy about what to do with the electrons. Okay, the next thing, and this is something that I don't know if I taught you or not, but today's a good day to learn it, and it's the difference in nuclear fission and fusion. I have to put down my notes for this because I always teach it this way. Oh, I should draw it on the board. That'll make it even better. All right, so fission, I say, imagine yourself, you've got a fish, because it sounds like fission. Okay, there's my fish. He's a happy fish, but he shouldn't be, because I want you to take out your knife, which is your hand, and I want you to imagine a fish and cut it in half. Always cut the fish in half, because fission is splitting an atom, and it's what results in bombs. It's because of E equals mc squared. Some of that mass gets changed to energy. It is splitting the atom. It's the atom bomb. You're splitting an atom and making a bomb. Now, there's a little more to it, but just for now, for this test, we're going to have a nuclear test. But for this test, this is all you need to know. Except you need to know what fusion is. F-U-S-S? I think it's just S-I-O-N. Fusion. It's sort of embarrassing to misspell science words on the thing, but I think that's right. But anyway, look, I'll just say it and then it won't be spelled there. Okay, so for fusion, I'm not good at spelling. It's because I'm dyslexic. All right. The letters, as Winnie the Pooh say, are wobbly. Okay, so this is how you remember. So fission, everybody do your hands like this. Imagine your fish. You're cutting it in half. Now, fusion is where little atoms, like hydrogen, are fused. You know what fused means? It means like put together. They're fused into bigger elements like helium. It's what's going on in the sun. And so I want you to imagine, you take your two hands and cup them together and make a ball, because you're making a big atom. So this is fusion, and you're making a ball, which then you turn into the sun, because that's what's going on in the sun. So in the sun, hydrogen is being fused into helium by the extreme gravity. That's my hand signal for gravity on the sun. All right, so fission and fusion. All right, that's all you have to know. This one is splitting the atom. This is squishing them together. All right. Yeah, I was right. Fusion only has one S, but I erased it because I was unconfident about my spelling there. All right, how to predict an ion by column, what the charge is going to be. All right, so if this column, this first column over here, becomes an ion, meaning, remember our hand signal for that is this. We're rubbing the electrons on or off. This is ion. I'm making a video, but y'all can come on in. Just be quiet. I told you that Miss Raymond was coming, and she's coming now. She's going to the book room. I'm making a review video, but I already warned them that you'd be coming in.
People are coming.
Yes, the people are coming. Anyway, so this is your question where you're going to pause it, is that in this first column, if it becomes an ion having electrons rubbed on or off, what charge is it positive or negative, and what charge is it? So I want you to pause the video and see if you can answer, what ion does this family become? Okay, are you back? It becomes +1 because it wants to lose one electron. So I want to walk over there and show you all the little things. I'll draw it. It wants to lose one electron. So here's the nucleus, and say this is a hydrogen that has a proton, and it's got